Every year the universe reveals something unexpected, but 2025 may be remembered as one of the most remarkable years yet. From distant exoplanets and ancient galaxies to strange cosmic signals and groundbreaking observations from NASA's newest missions, scientists are uncovering secrets that remained hidden for billions of years. Some discoveries answer old questions, others raise entirely new ones. Before we begin, don't forget to like this video and subscribe to the channel for more journeys through space science and the mysteries of the universe. Now let's take a closer look at NASA's newest discoveries of 2025. High above oceans, mountains, deserts, forests and cities, Earth appears in 2025 as a bright and slowly changing sphere surrounded by darkness. From orbital distance, the planet's atmosphere forms a thin, pale layer around the surface, faint compared with the size of the world below it. NASA satellites continue to circle Earth in overlapping paths, recording light, heat, moisture particles and motion across nearly every region of the globe. The work proceeds continuously and quietly, producing large streams of measurements that help researchers understand long-term planetary change rather than isolated events. The outermost view of Earth reveals patterns that are too large to recognize from the ground. Cloud systems stretch across oceans in long spirals. Dust moves outward from dry continental regions and drifts over water for thousands of kilometers. Seasonal snow expands and retreats across mountain ranges and polar landscapes. Ocean currents transport heat from tropical regions toward colder latitudes. These broad motions shape climate and weather over long periods of time. Observations from orbit allow these processes to be studied as connected parts of a single planetary system. NASA's Earth-observing satellites travel at different heights and along different orbital paths. Some move close to the planet and pass from pole to pole, allowing them to scan nearly the entire surface over repeated cycles. Others remain farther away in geostationary orbit, moving at the same rate as Earth's rotation and continuously observing the same hemisphere below. Together, these spacecraft create an uninterrupted record of changing atmospheric and surface conditions. The atmosphere itself appears calm from a great distance, yet measurements reveal constant movement within it. Sunlight warms Earth unevenly because the planet is curved and tilted. Tropical regions receive more direct solar energy than polar regions. Air warmed near the equator rises and begins moving toward cooler latitudes. Cooler air sinks and flows back toward warmer areas. Earth's rotation bends these moving air masses into large circulation systems that guide storms, moisture, and heat around the globe. Researchers use satellite instruments to measure temperature at different heights in the atmosphere. These instruments detect forms of light beyond normal human vision, including infrared radiation, which carries information about heat. By studying these measurements over long periods, scientists track gradual warming trends, seasonal shifts, and changing circulation patterns. Observations indicate that average global temperatures remain elevated compared with earlier industrial centuries. The exact regional effects continue to vary across the planet, and researchers study these differences carefully. Large cloud formations reveal the structure of atmospheric motion. Tropical storms appear over warm ocean water where evaporation transfers heat and moisture upward into the air. Spiral bands of clouds wrap around low-pressure centers and slowly organize into rotating systems. Satellite imagery allows scientists to observe these storms continuously as they strengthen, weaken, or change direction. Some storms dissipate harmlessly over open ocean, while others approach coastlines carrying heavy rainfall, strong winds, and storm surges. Farther from tropical regions, long bands of fast-moving air called jet streams circle the planet at high altitude. These currents help guide storms across continents and oceans. Satellite measurements combined with atmospheric models allow researchers to study how the position and strength of jet streams shift through the seasons. Observations suggest that warming conditions in polar regions may influence some patterns of atmospheric circulation, although the full complexity of these relationships remains under study. Above the oceans, satellites monitor sea surface temperatures with high precision. Warm water expands slightly and contributes to gradual sea level rise. Melting land ice also adds water to the oceans. Radar instruments measure the height of the sea surface across large distances, allowing researchers to detect long-term trends measured over decades. The increase remains uneven because ocean currents, winds, and gravitational effects influence regional conditions differently. Clouds over the oceans also reveal the movement of water through Earth's climate system. Water evaporates from warm seas, rises into cooler air, condenses into droplets, and later falls as rain or snow. This circulation transfers heat and moisture continuously around the world. Satellites track rainfall rates, cloud thickness, and atmospheric moisture content. These observations improve scientific understanding of droughts, floods, and long-term climate cycles. Overland orbiting instruments observe forests, grasslands, wetlands, and agricultural regions. Healthy vegetation reflects and absorbs light differently from dry or damaged plants. By studying these light patterns, researchers estimate plant growth and seasonal change across vast areas. Forest fires also become visible from orbit through thermal signatures and smoke plumes extending into the atmosphere. Some fires occur naturally after lightning strikes, while others are linked to human activity and prolonged dry conditions. In polar regions, the seasonal expansion and retreat of sea ice remain important areas of study. Arctic sea ice reaches its maximum extent during colder months and declines during warmer seasons. Long-term satellite records indicate that average Arctic sea ice coverage has decreased over recent decades. Antarctic sea ice shows more complex patterns that vary from year to year and across different regions. Researchers continue studying ocean circulation, atmospheric conditions, and temperature changes to better understand these variations. From orbital distance, cities appear as concentrated patterns of light during Earth's night side. Urban areas release heat differently from surrounding land because concrete asphalt and buildings absorb solar energy during the day and release it slowly after sunset. Satellites equipped with thermal instruments measure these temperature differences and help researchers study urban heat effects. Human activity also influences atmospheric composition through emissions of carbon dioxide, methane, and other gases that trap heat within the atmosphere. The Sun constantly interacts with Earth from beyond the atmosphere. Solar radiation provides energy for atmospheric circulation, ocean currents, and life itself. At times, the Sun also releases bursts of charged particles and magnetic energy that travel outward through space. Earth's magnetic field deflects much of this incoming material, protecting the atmosphere and surface from direct exposure. Satellites monitor solar activity closely because intense events can interfere with communication systems, navigation signals, and electrical infrastructure. Across 2025, NASA continues integrating observations from older spacecraft with data from newly launched missions. The goal remains steady and methodical rather than dramatic. Scientists compare measurements across years and decades, searching for gradual trends hidden within natural variation. Earth from orbit appears peaceful and silent, yet every cloud-band ocean, current, ice sheet, and atmospheric layer participates in continuous motion, shaped by gravity, sunlight, water, and time. Beyond the atmosphere, the region surrounding Earth contains thousands of active spacecraft and many more inactive objects moving through orbital paths at extraordinary speed. In 2025, this near-Earth environment remains one of the most carefully monitored regions of space. NASA, together with international agencies and research organizations, tracks satellites, scientific observatories, communication systems, weather platforms, navigation networks, and fragments of debris left behind by decades of launches. From a distance, the region appears empty, yet measurements reveal a constantly shifting structure of motion surrounding the planet. Low Earth orbit contains many of the satellites responsible for Earth observation and scientific research. These spacecraft circle the planet in roughly 90 minutes, moving fast enough to remain in continuous free fall around Earth rather than descending through the atmosphere. The orbital paths intersect at many angles and heights, creating a layered environment where each spacecraft must be monitored carefully to avoid collisions. The International Space Station continues operating in low Earth orbit during 2025. The station travels through alternating daylight and darkness many times each day as Earth rotates below it. Astronauts aboard the station conduct experiments involving biology, fluid motion combustion materials science, and the long-term effects of microgravity on the human body. Microgravity describes the condition in which objects experience continuous free fall, producing the sensation of weightlessness inside orbiting spacecraft. The station also serves as a platform for observing Earth itself. From orbital altitude, astronauts and instruments record cloud structures, storms, atmospheric glow, wildfire, smoke, and city lights. These observations complement satellite measurements by providing additional visual records of changing planetary conditions. The station remains one of the clearest examples of long-duration human activity beyond Earth's atmosphere. Farther outward, many scientific satellites operate in carefully selected orbits designed for specialized measurements. Some monitor the Sun, continuously studying solar radiation and magnetic activity. Others observe distant stars, galaxies, and high-energy cosmic events without interference from Earth's atmosphere. Space-based telescopes detect forms of light that are partially blocked before reaching the ground, including ultraviolet radiation X-rays and portions of infrared light. NASA's James Webb Space Telescope continues operating far beyond low Earth orbit near a location known as the second Lagrange point. A Lagrange point is a region where gravitational forces and orbital motion combine to allow spacecraft to remain relatively stable with minimal fuel use. From this distant position, the telescope observes ancient galaxies, exoplanets, stellar nurseries, and cold clouds of gas and dust with exceptional sensitivity. Although physically distant from Earth, the telescope remains connected through carefully timed communication systems. Closer to Earth, many satellites contribute to navigation and communication systems used daily across the planet. Navigation satellites broadcast timing signals that allow receivers on Earth to calculate position with remarkable accuracy. Communication satellites relay television broadcasts, telephone signals, internet traffic, and scientific data between distant locations. Some satellites remain fixed relative to Earth's surface by orbiting at geostationary altitude more than 35,000 kilometers above the equator. This higher orbital region appears less crowded visually, yet spacecraft there occupy valuable positions that must be coordinated carefully. At geostationary altitude, a satellite circles Earth at the same speed that Earth rotates, allowing it to remain above one location continuously. Weather satellites in this region provide uninterrupted views of cloud systems, hurricanes, and atmospheric circulation across entire hemispheres. Alongside active spacecraft, orbital debris continues accumulating as a long-term challenge. Debris includes fragments from rocket stages, inactive satellites, paint particles, broken components, and material generated during accidental or intentional collisions. Even small fragments travel at speeds capable of damaging operational spacecraft. Radar systems and optical telescopes monitor many of these objects continuously, calculating their future paths and warning operators about possible close approaches. Most orbital debris remains too small to track individually. Tiny particles strike spacecraft surfaces regularly, gradually eroding exposed materials over time. Engineers design satellites and stations with protective shielding to reduce risk from these impacts. Observations indicate that debris populations remain highest in heavily used orbital regions. International discussions continue regarding methods to reduce future accumulation, including controlled satellite disposal and improved launch practices. The upper atmosphere still affects objects in low Earth orbit despite the extreme altitude. Very thin traces of gas create drag that slowly reduces orbital height. During periods of stronger solar activity, the upper atmosphere warms and expands slightly, increasing drag on satellites and debris. Objects eventually descend low enough for atmospheric friction to generate intense heat, causing most material to burn apart before reaching the surface. Larger components occasionally survive partial re-entry and fall into remote ocean regions. NASA also studies the invisible environment surrounding Earth's magnetic field. Charged particles from the Sun interact with Earth's magnetosphere, the region controlled by planetary magnetism. Some particles become trapped within zones called the Van Allen radiation belts. These regions contain energetic particles that can damage spacecraft electronics and pose risks to astronauts outside Earth's protective atmosphere. Specialized satellites monitor radiation levels and magnetic disturbances continuously. Solar eruptions sometimes send large clouds of charged particles outward through space. When these clouds reach Earth, they can disturb magnetic fields and produce auroras near polar regions. Auroras form when charged particles interact with gases in the upper atmosphere, creating faint glowing curtains of light. Strong solar storms can also interfere with satellites' radio communication and electrical systems. Commercial activity in near-Earth orbit expands steadily during 2025. Private companies launch communication networks, cargo spacecraft, and experimental vehicles at increasing rates. Reusable rocket technology lowers launch costs by allowing some rocket stages to return safely for later use. These developments increase access to orbit while also raising concerns regarding traffic management, debris generation, and long-term sustainability. Human presence beyond Earth remains physically fragile despite decades of engineering progress. Spacecraft depend on carefully balanced systems for oxygen temperature control, radiation shielding, and communication. Outside protective structures, the environment of space exposes materials and living organisms to vacuum radiation and extreme temperature differences between sunlight and shadow. Yet from orbital distance, Earth still dominates the surrounding region visually. The planet's oceans, clouds, and illuminated atmosphere appear bright against the blackness beyond. Near-Earth space remains a transitional zone between the familiar conditions of Earth and the far more hostile environments deeper within the solar system. In 2025, NASA's growing network of spacecraft continues moving silently through this region, measuring, communicating, observing, and maintaining humanity's expanding presence just beyond the atmosphere. Beyond the crowded orbital region surrounding Earth, the Moon moves through space with slow regularity, reflecting sunlight across the darkness between worlds. In 2025, the Moon once again becomes a central focus of NASA exploration. Robotic missions, orbital observations, engineering tests, and Artemis preparations continue building a long-term understanding of the lunar environment. From a distance, the Moon appears still and unchanging, yet detailed measurements reveal a complex landscape shaped by impacts, radiation, temperature extremes, and ancient geological history. The Moon orbits Earth at an average distance of roughly 380,000 kilometers. Its gravitational influence helps stabilize Earth's rotational tilt and contributes to ocean tides. Unlike Earth, the Moon possesses no thick atmosphere to soften incoming impacts or distribute heat evenly across the surface. Sunlit regions become extremely hot during the lunar day, while shadowed areas cool to temperatures far below freezing during the long lunar night. From orbit, large dark plains stand out clearly against brighter highland terrain. These dark regions formed billions of years ago when molten rock flooded enormous impact basins and later cooled into solid volcanic plains. Early astronomers once believed these smooth regions were seas, leading to names that remain in use today, despite the absence of liquid water. The brighter highlands surrounding them contain older crust marked by dense concentrations of impact craters. NASA orbiters continue mapping the lunar surface with increasing precision. Laser instruments measure elevation changes across mountains, valleys, crater walls, and lava plains. Cameras capture detailed images of boulders, ridges, and fine surface textures. Spectrometers analyze reflected light to identify minerals and chemical composition. Together, these measurements help researchers reconstruct the Moon's geological history layer by layer. The lunar surface remains covered by regolith, a loose layer of dust and fragmented rock created by billions of years of impacts. Without atmosphere or weather, the Moon preserves evidence of collisions over immense stretches of time. Tiny meteoroids continue striking the surface regularly, slowly grinding rocks into finer particles. Lunar dust appears soft from a distance, but contains sharp microscopic edges, because erosion from wind and water never smooths the grains. During the Apollo missions, astronauts observed how strongly this dust clung to equipment and spacesuits. In 2025, NASA engineers continue studying methods to reduce dust accumulation, because long-term lunar exploration depends on maintaining machinery habitats and scientific instruments under difficult surface conditions. Dust particles can damage seals, scratch surfaces, and interfere with mechanical systems. Attention increasingly focuses on the Moon's polar regions, especially areas near permanently shadowed craters. Because the Moon's axis tilts only slightly, some crater floors near the poles never receive direct sunlight. Temperatures inside these regions remain extremely low for billions of years. Observations from orbit indicate that water ice exists within some of these shadowed environments, mixed with dust and rock. Scientists study this ice carefully because water supports several important functions in space exploration. Water provides drinking supplies, oxygen for breathing, and hydrogen that can be used as rocket fuel after chemical processing. Observations indicate that ice deposits vary greatly between locations, and researchers continue working to determine their exact concentration, depth, and accessibility. The Artemis program represents NASA's effort to establish a sustained human presence near and eventually on the lunar surface. Unlike the earlier Apollo missions, which involved short visits, Artemis planning emphasizes longer duration operations, international cooperation, and gradual infrastructure development. In 2025, testing continues for spacecraft systems, landing technologies, life support equipment, and navigation methods required for future crewed missions. The Orion spacecraft remains central to these plans. Designed for deep space travel, Orion supports astronauts during missions beyond low Earth orbit. The spacecraft includes systems for life support, communication, radiation protection, and controlled re-entry through Earth's atmosphere after returning from lunar distance. Engineers continue evaluating performance data from earlier missions, while refining systems for future crewed flights. Near the Moon itself, robotic landers contribute scientific measurements and technology demonstrations. Some missions study soil composition and thermal properties. Others test autonomous navigation systems, drilling equipment, or methods for surviving the long lunar night. Commercial lunar missions also increased during this period, with private companies delivering instruments and experimental hardware to the surface. The Moon's lack of atmosphere allows direct exposure to space weather and radiation from the Sun. Solar particles strike the surface continuously, gradually altering surface materials through a process called space weathering. Over time, this exposure darkens and chemically changes lunar soil. Instruments study these effects closely because they influence both scientific interpretation and the durability of future equipment. Radiation exposure remains one of the major concerns for long-term human activity on the Moon. Earth's atmosphere and magnetic field provide strong protection against energetic particles, but the lunar surface lacks these natural shields. Researchers investigate methods for reducing exposure, including habitat placement shielding materials and the possible use of underground lava tubes. Lava tubes are long, hollow channels formed by ancient volcanic flows. Some may remain stable beneath the surface and could provide natural protection from radiation and temperature extremes. The Moon also serves as a scientific archive of early solar system history. Earth's active geology and atmosphere erase many ancient impact records over time, but the Moon preserves them with far less alteration. By studying crater distributions and rock samples, scientists estimate the timing of major impact events that affected the inner solar system billions of years ago. Astronomers also consider the lunar far side an unusually quiet environment for radio observations. Earth produces large amounts of radio interference from communication systems and electrical activity, but the Moon blocks much of this noise on its far side. Future observatories placed there could study faint cosmic signals that are difficult to detect near Earth. From a distance, the Moon continues appearing calm and silent, its surface marked by light and shadow beneath unfiltered sunlight. Yet in 2025 it becomes increasingly active as a destination for scientific study and technological preparation. NASA's renewed lunar focus transforms the Moon from a distant object of observation into a nearby environment where long-term exploration slowly takes shape across dust, ice, stone, and darkness. Far beyond the Moon, Mars moves around the Sun within a colder and thinner region of the inner solar system. In 2025, NASA spacecraft continue circling the planet, observing its atmosphere climate patterns, surface chemistry, and seasonal changes from orbit. From great distance, Mars appears reddish because iron-rich minerals cover much of its surface. Closer observation reveals shifting clouds, frozen polar caps, enormous dust storms, and a landscape shaped by ancient interactions between rock, wind, water, and ice. Mars possesses a much thinner atmosphere than Earth. Surface pressure remains less than 1% of Earth's average atmospheric pressure, and carbon dioxide forms the majority of the atmospheric gas. Small amounts of nitrogen, argon, oxygen, and water vapor are also present. Because the atmosphere is so thin, heat escapes easily into space after sunset, causing large temperature differences between day and night. Orbiting spacecraft study these atmospheric conditions continuously. Instruments measure temperature, pressure, wind speed, dust concentration, and the movement of water vapor through the atmosphere. These measurements help scientists understand how Mars changes through its seasons, which are longer than Earth's, because Mars requires nearly 2 Earth years to complete one orbit around the Sun. The planet's tilted axis creates seasonal cycles similar in principle to those on Earth. During winter, at one pole, carbon dioxide from the atmosphere freezes directly onto the surface, forming seasonal frost and expanding the polar ice caps. During spring and summer, sunlight warms these regions and the frozen carbon dioxide returns to the atmosphere as gas. This annual exchange changes atmospheric pressure across the entire planet. The polar regions contain both seasonal frost and long-lasting ice deposits. Water ice lies beneath layers of dust and frozen carbon dioxide in many areas. Radar instruments aboard orbiters penetrate below the surface and reveal buried layers that preserve records of ancient climate changes. Scientists study these layered deposits much as researchers on Earth study ice cores from Antarctica and Greenland. Different layers may represent long periods of changing dust accumulation, atmospheric conditions, and ice stability. Thin clouds also form in the Martian atmosphere. Some contain water ice crystals, while others contain frozen carbon dioxide particles at higher altitudes. These clouds drift across the sky in delicate formations shaped by atmospheric circulation. Although visually gentle, the atmosphere also supports powerful dust activity, capable of affecting nearly the entire planet. Dust plays a central role in Martian climate. Fine particles cover broad regions of the surface and are easily lifted by wind. Local dust storms occur frequently, especially during warmer seasons when sunlight heats the surface strongly. At times, these storms grow larger and merge into regional systems. Occasionally, dust spreads across nearly the entire planet, reducing sunlight reaching the ground for weeks or months. Orbiters monitor these storms carefully because airborne dust changes atmospheric temperature and circulation. Dust absorbs sunlight during the day and influences how heat moves through the atmosphere. Large storms also affect solar-powered spacecraft operating on the surface by reducing available light. Observations indicate that global dust storms occur irregularly, and researchers continue studying why some storms expand dramatically, while others remain localized. Mars lacks a strong global magnetic field like Earth's. Measurements suggest that the planet once possessed a stronger magnetic environment billions of years ago, but this field weakened over time. Without strong magnetic protection, solar wind gradually strips away portions of the upper atmosphere. NASA's MAVEN spacecraft studies this ongoing atmospheric escape process by measuring interactions between solar particles and the upper atmospheric layers. Observations indicate that Mars likely possessed a thicker atmosphere and more stable surface water in its distant past. River valleys, delta formations, sediment deposits, and minerals formed in the presence of water support this conclusion. However, the exact timeline and duration of wetter conditions remain areas of active research. Scientists continue examining how rapidly atmospheric loss occurred and how long ancient lakes or rivers persisted. From orbit, ancient river channels remain visible across many regions. Some channels branch like river systems on Earth, suggesting long periods of flowing water erosion. Other landscapes contain signs of catastrophic floods that once released enormous volumes of water across the surface. Large impact basins also preserve evidence of ancient lakes that may have existed billions of years ago. Volcanoes dominate several regions of Mars. Olympus Mons rises far above surrounding plains and remains the largest known volcano in the solar system. Its broad shield shape forms through repeated lava flows spreading gradually outward over long periods. Nearby volcanic provinces contain many additional volcanoes, lava channels, and fractured terrain. Mars experiences little plate tectonic activity compared with Earth, allowing volcanic structures to remain in one location for immense spans of time. The atmosphere also interacts with the surface through wind erosion. Dust devils travel across dry plains, lifting columns of dust high into the air. Sand dunes migrate slowly over years and decades, shaped by prevailing winds. Orbiters repeatedly photograph these dunes, allowing scientists to track their movement and better understand modern atmospheric dynamics. High above the surface, thin atmospheric layers glow faintly under solar radiation. Orbiters observe auroras as well, although they differ from Earth's polar auroras because Mars lacks a strong global magnetic field. Some Martian auroras occur near localized crustal magnetic regions preserved within ancient rocks. These observations help researchers understand how charged particles interact with the remaining magnetic structures. Communication between Mars spacecraft and Earth requires careful timing, because radio signals travel across millions of kilometers of space. Depending on planetary positions, signals may require several minutes or much longer to cross the distance. Orbiters often relay communications between surface missions and Earth, forming a network that supports ongoing exploration. In 2025, Mars remains dry-cold and exposed beneath its thin atmosphere, yet orbital observations continue revealing traces of a more active ancient world. Dust circulates through the sky, frost grows and retreats across the poles, and buried ice preserves long climate records beneath the surface. NASA's orbiters move silently above these changing patterns, examining the planet layer by layer from the upper atmosphere down toward the ancient terrain below. Below the thin atmosphere of Mars, the planet's surface stretches outward in wide plains, fractured valleys, ancient lake beds, volcanic slopes, and fields of scattered stone. In 2025, NASA rovers continue moving slowly across selected regions, studying rocks and soil directly at ground level. These machines operate carefully within harsh environmental conditions shaped by cold temperatures, dust radiation, and low atmospheric pressure. Their observations reveal details too small and too local for orbiters alone to examine, allowing scientists to study the history of Mars through individual layers of sediment, mineral grains, and chemical traces preserved in stone. The Perseverance rover remains active inside Jezero crater, a basin believed to have once contained a lake billions of years ago. Orbital observations before landing identified features resembling an ancient river delta, where flowing water may have deposited mud, sand, and minerals over long periods. From the ground, the crater reveals cliffs, layered outcrops, loose sediment, and scattered boulders shaped by both ancient water activity and later wind erosion. Sedimentary rock forms an important focus of rover investigations. Sedimentary rock develops when particles settle gradually in water, wind, or other environments and later harden into stone. On Earth, these rocks often preserve evidence of ancient rivers, lakes, or oceans. The layered structures within Jezero crater strongly suggest long periods of deposition in standing or slowly moving water. Instruments aboard Perseverance examine these layers closely, identifying minerals and textures that help reconstruct the crater's environmental history. The rover carries cameras capable of detailed close-range imaging. These instruments reveal cracks, grain patterns, and mineral veins within Martian rocks. Some rocks contain fine laminations, thin repeated layers, that may have formed through quiet sediment accumulation in ancient water environments. Others display rounded grains shaped by transport through flowing water before settling into place. Chemical analysis instruments examine the elemental composition of surface materials. Sulfur, iron, magnesium, calcium, and silicon appear in varying combinations depending on the rock type and its formation history. Some minerals identified on Mars form most easily in the presence of water. Clay minerals, for example, develop through long interactions between rock and liquid water under relatively stable chemical conditions. Their presence supports evidence that parts of ancient Mars once remained wet for extended periods. NASA also studies organic molecules preserved within some Martian rocks. Organic molecules are carbon-containing compounds that can form through both biological and non-biological processes. Observations indicate that Mars contains organic chemistry in several regions, although no direct evidence of past life has been confirmed. Researchers approach these findings cautiously, focusing on understanding the environmental conditions that allowed such molecules to survive over immense timescales. Perseverance collects selected rock samples for possible future return to Earth. Small cores drilled from carefully chosen rocks are sealed inside metal tubes and deposited on the surface or stored aboard the rover. Scientists hope that future missions may eventually transport these samples back to Earth laboratories, where far more detailed analysis would become possible using equipment too large and delicate to send to Mars directly. Nearby, the Ingenuity helicopter originally demonstrated powered flight within the thin Martian atmosphere. Although its operational mission concluded after damage to its rotor system, the aircraft proved that controlled aerial exploration was possible under Martian conditions. The atmosphere on Mars remains so thin that flight requires extremely fast rotor speeds to generate enough lift. Ingenuity's success influences planning for future aerial vehicles that may explore terrain inaccessible to rovers. Elsewhere on Mars, the Curiosity rover continues operating within Gale Crater. This region contains Mount Sharp, a large central mountain composed of layered sediments, rising several kilometers above the crater floor. Curiosity studies these layers one by one while climbing gradually upward through the ancient deposits. Each layer records environmental conditions from different periods in Martian history. Curiosity's measurements reveal evidence that some ancient lakes within Gale Crater may have persisted for long durations. Fine mudstones, mineral chemistry and sediment structures indicate relatively calm water environments at certain times in the distant past. Other layers suggest changing climate conditions, including periods of drying and increased wind activity. Together, these records reveal that Mars experienced environmental transitions over millions of years rather than a single abrupt change. The Martian surface also preserves evidence of volcanic activity. Basaltic rock formed from cooled lava covers broad regions of the planet. Some lava plains remain relatively smooth, while others contain fractured surfaces and collapsed channels where molten rock once flowed. Meteorite impacts later reshaped much of this terrain, creating craters of many sizes scattered across nearly every region. Impact craters provide important clues regarding surface age. Regions containing many craters generally represent older surfaces because they have remained exposed longer to bombardment from space debris. Areas with fewer craters may have been resurfaced more recently through lava flows erosion or sediment deposition. Scientists combine crater counts with geological observations to estimate the relative ages of Martian landscapes. Wind continues shaping the planet today. Sand dunes migrate slowly across crater floors and plains under the influence of persistent atmospheric motion. Rovers photograph ripples and dunes repeatedly over time, revealing gradual movement of sand grains despite the thin atmosphere. Dust settles onto rover surfaces as well, sometimes reducing the efficiency of solar panels on older missions. Radiation exposure remains high at the Martian surface because the thin atmosphere and weak magnetic protection allow energetic particles from space to reach the ground more easily than on Earth. Instruments measure this radiation environment carefully because future human exploration depends on understanding long-term exposure risks. The sky above Mars often appears butterscotch or pale orange because fine dust suspended in the atmosphere scatters sunlight differently than Earth's atmosphere does. During sunset, the colors reverse in an unusual way, with bluish light concentrated near the sun while the surrounding sky darkens toward red and brown tones. These optical effects arise from the size and composition of airborne dust particles. In 2025, the surface of Mars remains silent except for wind moving across rock and sand beneath a thin, cold sky. Yet every drilled sample, photographed layer, and chemical measurement slowly deepens scientific understanding of the planet's long environmental history. NASA's rovers continue crossing ancient terrain meter by meter, studying the preserved remains of lakes, rivers, volcanic plains, and mineral deposits formed billions of years ago under conditions very different from those seen on Mars today. Far beyond the orbit of Mars, Jupiter dominates the outer solar system with immense scale and continuous atmospheric motion. In 2025, NASA spacecraft and Earth-based observatories continue studying the giant planet from a distance, examining its clouds, storms, magnetic environment, rings, and internal structure. Jupiter contains more mass than all the other planets combined, yet it remains composed mostly of hydrogen and helium, rather than solid rock. From afar, the planet appears as a banded sphere marked by shifting colors and enormous rotating storms beneath faint sunlight. Jupiter orbits the Sun at an average distance of more than 700 million kilometers from Earth's orbit. Sunlight reaching the planet remains far weaker than the sunlight received by Earth, yet Jupiter still radiates more heat than it absorbs. Observations indicate that heat slowly escapes from deep within the planet's interior, contributing to atmospheric circulation and storm activity visible at the cloud tops. The planet's atmosphere lacks a solid surface like Earth or Mars. Instead, pressure and temperature gradually increase with depth until gases become compressed into unusual states of matter. The visible cloud tops represent only the outermost layer of an enormous atmospheric envelope extending thousands of kilometers downward. Scientists continue studying how Jupiter's deeper structure behaves under such extreme pressure. Distinct cloud bands wrap around the planet parallel to the equator. Bright zones and darker belts form through powerful atmospheric circulation patterns driven by heat and rapid rotation. Jupiter rotates very quickly, completing one rotation in less than 10 Earth hours despite its enormous size. This rapid spin stretches atmospheric motion into long, east-west jet streams that separate neighboring cloud bands moving in opposite directions. NASA's Juno spacecraft continues orbiting Jupiter along a highly elongated path that repeatedly carries it close over the cloud tops before moving far outward again. Instruments aboard Juno measure gravity, magnetic fields, atmospheric composition, microwave emissions, and charged particles surrounding the planet. These measurements help scientists study structures hidden beneath the visible clouds. The colorful appearance of Jupiter's atmosphere arises from complex chemistry involving trace compounds mixed within hydrogen and helium gas. Ammonia ice forms many of the upper clouds, while deeper layers may contain ammonium hydrosulfide and water clouds. The exact chemical processes responsible for some color variations remain uncertain. Observations indicate that sunlight, atmospheric motion, and chemical reactions together influence the shifting patterns seen from orbit and telescopic views. The Great Red Spot remains one of Jupiter's most recognizable features. This enormous rotating storm has persisted for centuries, although its size and shape gradually change over time. The storm rotates counterclockwise and extends far above surrounding cloud layers. Winds within the system move at extraordinary speed, yet the storm slowly shrinks compared with earlier historical observations. Scientists continue studying why such storms form and how they remain stable for long periods. Smaller storms appear across many regions of the atmosphere. Some merge together while others dissipate. White oval storms drift through certain latitudes, and turbulent boundaries between cloud bands create constantly changing textures. Lightning also occurs deep within Jupiter's atmosphere. Instruments detect radio signals and flashes associated with large storms, suggesting that water clouds far below the upper layers contribute to electrical activity. Beneath the visible atmosphere, pressure increases rapidly with depth. Hydrogen gas eventually becomes compressed into liquid form. At still greater depth, scientists believe hydrogen enters a metallic state, conducting electricity under immense pressure. This layer likely plays a major role in generating Jupiter's powerful magnetic field through the movement of electrically conducting material deep inside the planet. Jupiter's magnetic field extends across enormous distances and traps intense radiation around the planet. Charged particles spiral through this environment at high energy levels, creating hazardous conditions for spacecraft. Juno travels through portions of this radiation environment during each orbit, and engineers carefully protect its electronics with specialized shielding. The planet's auroras glow continuously near the poles, far stronger than auroras on Earth. Charged particles funnel along magnetic field lines into the upper atmosphere, interacting with atmospheric gases and producing ultraviolet and infrared emissions. Some particles originate from the solar wind, while others come from Jupiter's moons, especially Io, whose volcanic activity releases material into surrounding space. Although Jupiter appears solitary from a distance, it possesses a faint ring system surrounding the planet. Unlike Saturn's bright icy rings, Jupiter's rings consist mainly of fine dust particles produced by impacts on small inner moons. These rings remain difficult to observe directly because they reflect relatively little sunlight. Spacecraft imaging reveals thin structures extending around the planet in delicate layers. Jupiter also exerts strong gravitational influence throughout the outer solar system. Its enormous mass affects the orbits of asteroids, comets, and smaller bodies. Some scientists suggest that Jupiter's gravity helped shape the early solar system by redistributing material during planetary formation. At times, the planet's gravitational pull redirects comets inward toward the Sun or outward into distant space. The planet's upper atmosphere extends gradually into surrounding space rather than ending abruptly. Interactions between magnetic fields, charged particles, and escaping atmospheric material create a vast surrounding environment called the magnetosphere. Jupiter's magnetosphere remains the largest planetary structure in the solar system, stretching millions of kilometers through space. Earth-based telescopes continue supporting spacecraft observations in 2025. Infrared imaging tracks heat patterns and storm development. Radio observations measure magnetic interactions. Spectroscopy studies atmospheric chemistry by analyzing absorbed and emitted light. Together, these observations allow scientists to monitor changes over time and compare conditions across different atmospheric layers. From great distance, Jupiter appears calm, luminous, and steady against the darkness of space. Closer study reveals constant turbulence beneath the cloud tops shaped by heat, gravity, pressure, chemistry, and magnetic energy operating on scales far beyond those found on Earth. NASA's continuing observations slowly uncover the structure of this giant world, layer by layer from the outer cloud bands down toward the hidden depths beneath them. Around Jupiter, a large family of moons moves through the giant planet's immense gravitational field. In 2025, NASA missions and telescope observations continue focusing especially on Europa, Ganymede, and Io, three worlds that differ greatly from one another despite orbiting the same planet. Their surfaces, internal structures, and interactions with Jupiter reveal environments shaped by ice radiation, gravity, and volcanic heat. From orbital distance, these moons appear small beside Jupiter itself, yet detailed observation shows that each contains complex geological processes, unlike those found elsewhere in the solar system. Europa reflects sunlight brightly because much of its surface consists of water ice. The moon's crust appears smooth compared with heavily cratered worlds, suggesting that geological activity has reshaped the surface over time. Long, dark fractures cross the icy terrain in branching patterns that extend for hundreds or even thousands of kilometers. Some ridges rise above the surrounding plains, while other regions contain broken blocks of ice that appear to have shifted and rotated before freezing again into place. Observations indicate that a global ocean of liquid water likely exists beneath Europa's frozen outer shell. Strong gravitational interactions with Jupiter create tidal forces that flex the moon continuously during its orbit. This repeated flexing generates internal heat through friction, helping prevent the subsurface ocean from freezing solid despite the moon's great distance from the sun. Scientists continue studying the thickness of Europa's ice shell. Measurements suggest that the outer crust may vary considerably between regions. In some areas, the ice could be relatively thin, while other areas may contain much thicker frozen layers. Radar instruments planned for future missions aim to examine structures beneath the surface, directly searching for pockets of liquid water, layered ice, and pathways through which subsurface material may occasionally reach the surface. Europa attracts particular scientific interest because liquid water energy sources and chemical compounds necessary for complex chemistry may all exist together beneath the ice. Observations indicate that salts and other materials may move between the ocean and surface through cracks or eruptions. However, it remains uncertain whether Europa's hidden ocean possesses conditions suitable for life. Researchers approach this question carefully, focusing first on understanding the moon's chemistry structure and energy balance. NASA's Europa Clipper mission continues preparation and early operational planning during 2025. The spacecraft is designed to perform repeated close flybys rather than orbiting Europa, directly reducing exposure to Jupiter's intense radiation environment. Instruments aboard the mission will examine ice structure, surface composition, magnetic interactions, and possible water vapor plumes extending above the surface. Farther outward orbits Ganymede, the largest moon in the solar system. Ganymede exceeds the size of the planet Mercury, although its composition differs greatly. The moon contains a mixture of rock and ice, and possesses a complex surface marked by both ancient cratered terrain and younger grooved regions. Bright linear features stretch across broad areas where tectonic forces once fractured and reshaped the icy crust. Unlike most moons, Ganymede possesses its own magnetic field. Observations suggest that electrically conducting liquid material deep inside the moon generates this field through internal motion. The magnetic field interacts with Jupiter's larger magnetosphere, creating auroral patterns near the poles. Measurements of these auroras provide indirect evidence regarding the structure and depth of Ganymede's suspected subsurface ocean. Scientists believe several layers of ice and liquid water may exist beneath Ganymede's surface. Pressure conditions deep below the crust likely create unusual forms of ice denser than the familiar ice found on Earth. The moon's internal structure remains an active area of research because understanding how water, rock, and heat interact within such large icy worlds may help scientists interpret similar objects elsewhere in the solar system and beyond. Ganymede's surface records a long geological history. Heavily cratered dark regions preserve evidence of ancient impacts from the early solar system, while younger grooved terrain suggests later tectonic deformation. Some grooves may have formed as internal stresses pulled sections of crust apart, allowing warmer material from below to alter the surface structure gradually over immense spans of time. Closer to Jupiter lies Io, the most volcanically active known world in the solar system. Its surface appears covered in yellow, orange, black and white deposits created by sulfur compounds and volcanic materials. Unlike icy Europa and Ganymede, Io contains little water. Instead, intense tidal heating generated by Jupiter's gravity continually melts portions of the Moon's interior, driving widespread volcanic activity. Volcanoes on Io erupt lava and gases hundreds of kilometers above the surface. Some volcanic plumes spread outward in umbrella-shaped patterns before falling back onto the ground as frost-like deposits. Surface features change rapidly compared with most planetary bodies because eruptions continuously reshape the landscape. Lava lakes, flowing molten rock, collapsing crust, and fresh volcanic deposits appear across many regions. Infrared observations detect intense heat from active volcanic centers. Scientists monitor these regions to understand how tidal heating operates inside the Moon. Io's interior experiences constant flexing as gravitational forces vary during its slightly elliptical orbit. This mechanical stress produces enough internal heat to sustain extraordinary volcanic activity across the surface. Material escaping from Io also affects Jupiter's broader environment. Volcanic gases become ionized and trapped within Jupiter's magnetic field, contributing to large radiation belts and plasma structures surrounding the planet. In this way, Io participates directly in the dynamics of the Jovian system, rather than remaining isolated from its surroundings. The radiation environment near Jupiter remains severe for spacecraft exploring these moons. High-energy particles can damage electronics and interfere with instruments. Engineers designing missions to the Jovian system must account carefully for radiation exposure while planning orbital paths and observation schedules. Together, Europa, Ganymede, and Io reveal three very different outcomes of planetary evolution shaped under the same giant planet's influence. Ice-covered oceans, tectonic crusts, hidden magnetic fields, and erupting volcanoes exist within a single moon system, orbiting deep in the outer solar system. In 2025, NASA observations continue uncovering details of these worlds, slowly and methodically examining how gravity, heat, water, and rock interact beneath their distant surfaces. Beyond Jupiter, the outer solar system becomes colder, darker, and more widely spaced. Saturn, Uranus, and Neptune move through distant orbital paths where sunlight weakens and temperatures fall far below those of the inner planets. In 2025, NASA observatories and international telescope networks continue studying these giant worlds from afar, examining their atmospheres, rings, seasonal cycles, magnetic fields, and internal heat. Although spacecraft no longer orbit these planets directly, modern instruments provide increasingly detailed observations that reveal steady processes unfolding across immense distances. Saturn appears as a pale golden sphere surrounded by broad rings of ice and dust. The planet itself consists mainly of hydrogen and helium, similar to Jupiter, though smaller and less massive. Strong winds circle the atmosphere in wide bands, and storms occasionally disturb the otherwise layered appearance of the cloud tops. Saturn radiates additional heat from its interior, contributing to atmospheric motion, despite the weak sunlight reaching the planet. The ring system remains Saturn's most recognizable feature. Countless particles of ice rock and dust orbit the planet in thin, flattened layers extending hundreds of thousands of kilometers outward. Individual particles range from microscopic grains to objects several meters across. The rings appear bright because water ice reflects sunlight efficiently. Observations from the Cassini mission continue providing scientific data long after the spacecraft's mission ended, and researchers in 2025 still analyze measurements gathered during its years in orbit. The rings are not solid structures. Instead, each particle follows its own orbital path around Saturn. Gravitational interactions between ring particles and nearby moons create gaps, waves, and delicate spiral structures throughout the system. Some small moons orbit within ring gaps and help maintain sharp boundaries through their gravitational influence. These interactions reveal how gravity shapes matter in rotating systems on many scales throughout the universe. Scientists continue studying the age and long-term stability of Saturn's rings. Observations suggest that ring material gradually falls into the planet's atmosphere through interactions with magnetic fields and charged particles. This slow process, sometimes called ring rain, transfers water and dust into the upper atmosphere. It remains uncertain exactly when the rings formed or how long they will persist in their present form. Saturn's atmosphere contains ammonia clouds in upper layers and likely deeper water clouds farther below. Large storms occasionally emerge and spread around the planet. One persistent atmospheric feature near the North Pole forms a hexagonal pattern first observed decades ago and still visible in modern observations. The hexagon arises from atmospheric flow patterns shaped by Saturn's rapid rotation and jet streams, though researchers continue refining models explaining its long-term stability. Many moons orbit Saturn, each contributing to the complexity of the system. Titan, the largest moon, possesses a thick nitrogen-rich atmosphere and stable liquid methane and ethane on its surface. Lakes, rivers, clouds, and rainfall occur there, although involving hydrocarbons rather than water, due to the extremely cold temperatures. Observations indicate that Titan's chemistry resembles some conditions that may have existed on early Earth before life developed. NASA continues preparing for the Dragonfly mission during 2025. This rotorcraft mission aims to explore Titan's surface and atmosphere directly in the coming years. Engineers design the craft to fly through Titan's dense atmosphere, where lower gravity and thick air make powered flight more efficient than on Earth. Scientists hope the mission will examine organic chemistry, surface materials, and environmental conditions across multiple locations. Farther from the Sun, Uranus appears pale blue-green because methane in its atmosphere absorbs red light and reflects shorter wavelengths. Unlike the larger Jupiter and Saturn, Uranus rotates in an unusual orientation, tilted dramatically relative to its orbit. The planet essentially spins on its side, causing extreme seasonal variations as different hemispheres experience decades of sunlight followed by decades of darkness. The atmosphere of Uranus appears relatively calm compared with Jupiter and Saturn, yet detailed infrared and visible light observations reveal storms, clouds, and atmospheric circulation patterns. Winds move through upper atmospheric layers while heat slowly escapes from the interior. Uranus emits surprisingly little excess internal heat compared with other giant planets, and scientists continue studying why its internal structure behaves differently. Uranus also possesses faint rings composed of dark material that reflects little sunlight. These rings remain narrow and difficult to observe without sensitive instruments. The planet's magnetic field adds further complexity because it is tilted and offset significantly from the planet's center. As Uranus rotates, the magnetic environment twists into unusual shapes, unlike those surrounding other major planets. Still farther outward lies Neptune, the most distant major planet in the solar system. Neptune shares a similar blue appearance with Uranus because methane also exists within its atmosphere. However, Neptune displays more vigorous atmospheric activity despite receiving even less solar energy. Powerful winds race through the atmosphere at speeds exceeding those measured on any other planet in the solar system. Large storms appear and disappear across Neptune's cloud tops over time. Some resemble dark oval systems similar in appearance to storms on Jupiter, though shorter-lived. Bright methane ice clouds form at high altitude where rising gas cools and condenses. Neptune also radiates substantial internal heat, which likely contributes to its dynamic atmosphere and strong winds. Neptune's moon, Triton, orbits in a direction opposite the planet's rotation, suggesting that it may once have been an independent object captured by Neptune's gravity. Triton contains nitrogen ice-frozen water and signs of geological activity. Observations from earlier spacecraft detected dark plumes rising above the surface, indicating that some internal processes may still remain active beneath the frozen crust. In 2025, much of what is known about Uranus and Neptune still depends heavily on the Voyager missions from the late 20th century, combined with increasingly advanced telescope observations from Earth and space. Scientists continue proposing future missions that could study these distant planets directly once again. Their remote positions make exploration slow and technically demanding, requiring many years of travel through deep space. Across the outer giant planets, sunlight fades into a dim, steady glow. Rings drift silently around Saturn. Methane clouds move across Uranus and Neptune, and internal heat slowly rises through deep atmospheric layers hidden beneath thick clouds. NASA's observations continue from far away, gathering light, temperature, and spectral measurements that slowly reveal the structure and behavior of these cold, distant worlds. Beyond Neptune, the solar system opens into a broad region filled with frozen bodies orbiting slowly in deep, cold darkness. This distant zone, known as the Kuiper Belt, contains dwarf planets, icy fragments, and ancient material preserved from the early formation of the solar system. In 2025, NASA telescopes and continuing analysis from earlier missions study these remote objects carefully because they preserve conditions that change little over billions of years. Sunlight at these distances becomes weak and pale, illuminating worlds where temperatures remain far below freezing and geological activity proceeds slowly, if at all. The Kuiper Belt begins beyond Neptune's orbit and extends outward for billions of kilometers. Unlike the dense asteroid belt between Mars and Jupiter, the Kuiper Belt remains extremely spread out. Objects orbit the Sun with large separations between them, making collisions relatively rare despite the vast number of bodies present. Most Kuiper Belt objects contain mixtures of ice rock and organic compounds, frozen solid under intense cold. Pluto remains the most familiar object in this distant region. Once classified as the 9th planet, Pluto is now recognized as a dwarf planet because it shares its orbital region with many similar bodies. Observations from NASA's New Horizons mission continue providing valuable scientific information long after the spacecraft's flyby. The images and measurements revealed a world far more active and varied than many scientists expected before the mission. Pluto's surface contains nitrogen ice, methane, ice water, ice mountains, plains, valleys, and layered atmospheric haze. One broad, bright region, shaped roughly like a heart, became especially recognizable in spacecraft imagery. Within this area lies Sputnik Planitia, a vast basin filled with frozen nitrogen ice. The surface there appears unusually young because convection slowly reshapes the ice over time. Convection occurs when warmer material rises and cooler material sinks, creating gradual circulation within the frozen surface layer. Despite the extreme cold, Pluto shows evidence of internal activity. Observations suggest that heat trapped inside the dwarf planet may still influence portions of its interior. Some scientists propose that a subsurface ocean of liquid water may exist deep beneath the crust, insulated by layers of ice and radioactive heat from rocky material inside. However, the exact structure of Pluto's interior remains uncertain. Thin atmospheric haze surrounds Pluto when it moves closer to the Sun during part of its orbit. Nitrogen gas sublimates directly from surface ice into the atmosphere under weak sunlight. Sublimation describes the transition from solid to gas without passing through a liquid state. As Pluto travels farther from the Sun, much of this atmosphere freezes back onto the surface. This slow seasonal cycle unfolds across decades because Pluto requires more than 200 Earth years to complete one orbit. Nearby orbits Charon-Pluto's large moon. Charon is so large relative to Pluto that the two bodies revolve around a shared point located outside Pluto itself. The surfaces of both worlds display fractures, cliffs, and signs of geological evolution. Charon lacks Pluto's thick, volatile ice deposits, but still preserves evidence of ancient internal processes that shaped its crust long ago. Farther outward and across the Kuiper Belt, many other dwarf planets and icy bodies continue orbiting in darkness. Eris, Makemake, and Haumea represent some of the larger known examples. Each differs in composition, shape, rotation, and surface features. Haumea rotates unusually quickly, giving it an elongated shape rather than a near sphere. It also possesses a ring system, demonstrating that rings can form around surprisingly small bodies under suitable conditions. The surfaces of Kuiper Belt objects often appear reddish or darkened because radiation from the sun and cosmic rays alters surface chemistry over immense spans of time. Complex organic compounds gradually form as frozen methane, and other molecules break apart and recombine under energetic particle exposure. These materials, called tholins, contribute to the dark red colors observed on many distant icy bodies. NASA telescopes continue searching for additional Kuiper Belt objects in 2025. Many remain difficult to detect because they reflect little sunlight and move slowly against the background stars. Large surveys using sensitive digital instruments help astronomers identify faint moving objects through repeated observations over time. Each discovery contributes to understanding how the outer solar system formed and evolved. The Kuiper Belt also contains many short-period comets. These icy bodies occasionally move inward toward the Sun after gravitational interactions alter their orbits. As they approach warmer regions, sunlight heats surface, ice releasing gas and dust into space and forming glowing comas and tails. The material within these comets preserves chemical compounds from the early solar system, making them important scientific targets. Scientists believe the outer solar system changed significantly during its early history. Models suggest that the giant planets may have shifted orbital positions billions of years ago, redistributing smaller icy bodies across distant space. Some objects were ejected entirely from the solar system, while others became trapped within stable orbital resonances controlled by Neptune's gravity. Observations of Kuiper Belt orbits support aspects of these models, although details remain under active investigation. At the outer edge of the Kuiper Belt, sunlight weakens further into a dim point far brighter than surrounding stars but no longer dominant in the sky. Temperatures remain low enough for volatile substances such as nitrogen, methane, and carbon monoxide to exist as solid ice on many surfaces. Geological change proceeds extremely slowly under such conditions, preserving ancient structures for immense periods. The New Horizons spacecraft continues traveling outward through this distant region after its Pluto encounter. During its extended mission, the spacecraft studies additional Kuiper Belt objects and measures dust particles and conditions in the outer solar system. Each observation contributes small but valuable information about a region still only partially explored directly. In 2025, the Kuiper Belt remains a quiet outer frontier filled with frozen remnants from the solar system's formation. Ice-covered dwarf planets, dark organic surfaces, faint atmospheres, and slowly orbiting bodies preserve records from an ancient era long before Earth developed oceans or life. NASA's continuing observations examine these distant objects carefully, revealing that even the coldest and most remote regions of the solar system contain complex histories written across ice rock and time. Far beyond the Kuiper Belt, the influence of the Sun gradually weakens across an immense region where solar wind slows and interstellar space begins to dominate. In 2025, NASA continues studying this distant boundary, Through data returned by the Voyager spacecraft and through observations of the heliosphere, the vast bubble created by particles and magnetic fields flowing outward from the Sun. This outermost region of the solar system remains difficult to observe directly because of its enormous distance, yet it provides important information about how stars interact with the wider galaxy surrounding them. The Sun continuously releases a stream of charged particles called the solar wind. These particles flow outward in all directions at high speed, carrying magnetic fields far beyond the planets. Near Earth, the solar wind interacts with planetary magnetic fields and atmospheres, influencing auroras and space weather. Farther outward, the solar wind spreads through the giant planet region, and beyond the Kuiper belt, gradually slowing as it encounters material between the stars. This solar outflow creates the heliosphere, an enormous region surrounding the solar system. Inside the heliosphere, the solar wind remains the dominant influence on charged particles and magnetic conditions. Outside it, the interstellar medium becomes stronger. The interstellar medium consists of extremely thin gas-dust magnetic fields and energetic particles drifting between stars within the Milky Way galaxy. The boundary regions between these environments do not form a sharp wall. Instead, several transition zones exist where solar and interstellar influences interact gradually. One important boundary is the termination shock, where the solar wind slows from supersonic speeds due to pressure from the surrounding interstellar medium. Beyond this region lies the helios sheath, where slowed solar particles become more turbulent and compressed. Still farther outward lies the heliopause, often considered the outer edge of the heliosphere. At this boundary, the outward pressure of the solar wind balances against the inward pressure of interstellar space. Beyond the heliopause, interstellar particles and magnetic fields dominate. Measurements indicate that this boundary changes shape and position over time, depending on solar activity and local interstellar conditions. NASA's Voyager 1 and Voyager 2 spacecraft continue traveling through these distant regions in 2025. Launched in the late 1970s, both spacecraft first explored the outer planets before continuing outward toward interstellar space. Their long operational lifetimes remain among the most remarkable achievements in space exploration history. Voyager 1 crossed the heliopause first, followed later by Voyager 2. Instruments aboard the spacecraft detected changes in particle density, magnetic conditions, and cosmic ray intensity that indicated entry into interstellar space. Even so, the spacecraft remained gravitationally bound to the Sun and will continue moving through the Milky Way for immense spans of time. Communication with the Voyagers requires extraordinary patience because of the enormous distances involved. Radio signals travel at the speed of light, yet still require more than 20 hours to move one way between Earth and the spacecraft. The signals arriving at Earth become extremely faint after traveling billions of kilometers through space. Large radio antennas belonging to NASA's Deep Space Network receive these weak transmissions and relay scientific data back to researchers. Power aboard the Voyager spacecraft slowly decreases over time. Both probes rely on radioisotope thermoelectric generators, devices that convert heat from decaying radioactive material into electricity. As power levels decline, engineers gradually deactivate non-essential systems to preserve critical instruments and communication capability for as long as possible. The outer heliosphere also influences cosmic rays entering the solar system. Cosmic rays are highly energetic particles originating from supernovae, black holes, and other energetic processes throughout the galaxy. The heliosphere partially shields the inner solar system from some of these particles. Measurements from Voyager spacecraft show that cosmic ray intensity increases beyond the heliopause, where solar influence weakens. Scientists continue studying the shape of the heliosphere itself. Earlier models often described it as comet-like, with a long trailing tail extending behind the solar system as it moves through interstellar space. More recent observations suggest the structure may be more rounded or influenced strongly by magnetic fields. The exact shape remains uncertain because direct measurements exist only along the Voyager paths, leaving much of the surrounding region unobserved directly. Outside the heliosphere, interstellar space remains extraordinarily sparse by Earth standards. Even there, however, the environment is not empty. Thin clouds of hydrogen gas, microscopic dust particles, and magnetic fields drift between stars. Temperatures and particle densities vary across different regions of the galaxy. The solar system currently moves through a relatively thin interstellar cloud within the Orion arm of the Milky Way. NASA missions closer to Earth also contribute to heliosphere research. Spacecraft observing energetic neutral atoms help map interactions between solar and interstellar particles indirectly. These measurements reveal broad structures within the heliosphere that cannot be photographed directly because the region remains too diffuse and vast. The Sun's activity cycle also influences outer heliosphere conditions. During periods of high solar activity, stronger solar wind and magnetic disturbances propagate outward through the solar system. These effects may require many months or even years to reach the distant outer boundary regions because of the enormous scale involved. As Voyager spacecraft continue outward, they carry records of Earth and humanity within their golden phonograph records. These records contain sounds, images, music, and greetings selected to represent aspects of life on Earth. The spacecraft themselves become long-lasting objects drifting through the galaxy, long after communication eventually ends. In 2025, the outer edge of the solar system remains a region of transition where the Sun's influence slowly fades into the broader environment of the Milky Way. The solar wind weakens, cosmic rays intensify, and interstellar particles become more common. NASA's aging Voyager spacecraft continue moving silently through this distant darkness, measuring conditions at the boundary between the familiar domain of the Sun and the wider galaxy beyond. Beyond the outer boundary of the solar system, nearby stars emerge as individual systems rather than distant points of light alone. In 2025, NASA observatories continue studying stars close to the Sun and the planets orbiting around them. These exoplanets' worlds beyond the solar system vary greatly in size, temperature, composition, and orbital motion. Some orbit close to small red stars under intense heat, while others move through colder regions where water may remain liquid under suitable conditions. Observations remain careful and limited because the distances are immense, yet modern instruments increasingly reveal details about atmospheres, weather, and planetary structure far beyond the reach of direct travel. The nearest star system to the Sun is Alpha Centauri, located more than 4 light-years away. A light-year measures the distance light travels in 1 year through empty space. Even at the speed of light, signals require years to cross these distances. Human spacecraft using present technology would require many thousands of years to reach nearby stars directly, making telescope observation the primary method for studying them. Many nearby stars differ significantly from the Sun. Red dwarf stars remain especially common throughout the galaxy. These stars are smaller, cooler, and dimmer than the Sun, yet they often survive for extremely long periods because they consume fuel slowly. Observations indicate that planets frequently orbit red dwarf stars, and some systems contain several rocky worlds moving close to their parent stars. NASA's Transiting Exoplanet Survey satellite continues identifying exoplanets by observing tiny decreases in starlight brightness. This method, called the transit method, detects planets when they pass between their star and the observing telescope. The small drop in light reveals the planet's presence and allows scientists to estimate its size and orbital period. Repeated observations provide additional information about planetary systems. Some exoplanets orbit very close to their stars and complete one orbit within only a few days. Others move along more distant paths, requiring years or decades to complete a single orbit. In some systems, multiple planets orbit in carefully balanced gravitational relationships. The James Webb Space Telescope contributes significantly to exoplanet research in 2025. During planetary transits, a small portion of starlight passes through the exoplanet's atmosphere before reaching the telescope. Different gases absorb specific wavelengths of light, allowing scientists to identify atmospheric components indirectly through spectroscopy. Observations reveal atmospheres containing water, vapor carbon dioxide, methane, sodium, and other gases on some exoplanets. However, interpreting these signals remains difficult because measurements are extremely delicate and often involve very small changes in light. Scientists approach conclusions cautiously, especially when considering possible biological implications. Some exoplanets belong to categories not found in the solar system. Hot Jupiters, for example, are giant gas planets, orbiting extremely close to their stars. Their atmospheres become intensely heated, causing strong winds and expanded upper layers. Other planets known as super-Earths possess masses larger than Earth, but smaller than Neptune. The exact nature of these worlds varies widely depending on composition and atmospheric conditions. Researchers pay particular attention to planets orbiting within the habitable zone of their stars. The habitable zone refers to the range of distances where temperatures may allow liquid water to exist on a planet's surface under suitable atmospheric conditions. Being located within this zone alone does not guarantee habitability, since atmosphere magnetic protection geology and stellar activity also strongly influence planetary environments. Many red dwarf stars produce frequent stellar flares, releasing bursts of radiation and charged particles. Planets orbiting close to such stars may experience intense radiation exposure that could affect atmospheric stability. Observations indicate that stellar activity remains an important factor when evaluating whether environments might remain stable over long periods. NASA observatories also study the stars themselves in detail. Stellar brightness, temperature, composition, and age influence the formation and evolution of surrounding planets. Some stars contain higher concentrations of heavy elements than others, affecting the types of planets that form within their surrounding disks of gas and dust. Around young stars, astronomers observe protoplanetary disks, flattened structures composed of gas ice and dust particles. Within these disks, particles gradually collide and accumulate into larger bodies over millions of years. Rings, gaps, and spiral structures observed within some disks suggest that newly forming planets shape the surrounding material through gravity even before they become directly visible. Nearby stellar systems also help scientists compare planetary evolution with conditions in the solar system. Some systems appear highly compact, with several planets orbiting closer to their star than Mercury orbits the Sun. Others contain giant planets moving along highly elongated paths. These variations reveal that planetary systems can develop through many different arrangements. Interstellar distances remain immense despite these discoveries. Even the closest exoplanets remain unreachable with present human technology. For this reason, most information comes through careful interpretation of light. Slight changes in brightness, color, motion, and spectrum allow scientists to infer the existence and properties of worlds never directly visited. NASA's observations continue improving because telescope sensitivity increases steadily over time. Advanced instruments block starlight to reveal faint surrounding objects more clearly. Infrared observations detect heat signatures invisible to ordinary vision. Computer analysis combines repeated measurements gathered across months and years to strengthen confidence in subtle signals. In 2025, nearby stars no longer appear merely as distant lights without structure. Around many of them orbit complex planetary systems containing giant gas worlds, rocky planets, thick atmospheres, clouds, storms, and perhaps oceans beneath alien skies. Yet much remains uncertain. Observations indicate remarkable diversity across these systems, while the exact conditions on individual exoplanets often remain only partially understood. NASA's telescopes continue examining them patiently through faint starlight crossing the darkness between stars. Between the stars of the Milky Way, enormous clouds of gas and dust drift slowly through space. In 2025, NASA space telescopes continue observing these nebulae in great detail, revealing regions where stars and planetary systems gradually form. From a distance, nebulae appear as faint glowing patches or dark obscuring shapes against dense star fields. Closer observation shows complex structures shaped by gravity radiation, magnetic fields, turbulence, and time. Within these cold clouds, simple particles slowly gather into denser regions that may eventually ignite as new stars. Most nebulae consist primarily of hydrogen gas mixed with smaller amounts of helium dust grains and heavier elements created by earlier generations of stars. Dust particles remain extremely small, often comparable in size to smoke particles on Earth. Despite their tiny scale, dust grains strongly influence the appearance and chemistry of nebulae by absorbing, scattering, and re-emitting light. Some nebulae shine because nearby stars illuminate the surrounding gas. Ultraviolet radiation from hot young stars energizes hydrogen atoms, causing the gas to emit characteristic red light. Other nebulae remain dark because dense dust blocks starlight behind them. In infrared wavelengths, however, many of these dark clouds become partly transparent, allowing space telescopes to observe structures hidden within them. The James Webb Space Telescope continues transforming observations of star-forming regions during 2025. Infrared instruments penetrate dust clouds more effectively than visible light telescopes, revealing previously hidden stars, disks, and dense condensations. These observations provide detailed views of environments where planets may eventually emerge around young stars. Within large molecular clouds, gravity slowly draws material inward toward denser regions. Turbulence and magnetic fields complicate this process, creating filaments, knots, and layered structures throughout the cloud. Over long periods, some dense regions collapse further under their own gravity, forming protostars. A protostar is a young forming star that has not yet begun stable hydrogen fusion in its core. As material falls inward, conservation of angular momentum causes rotating disks to form around many protostars. These disks contain gas dust and ice particles orbiting the growing central object. Collisions within the disk gradually allow particles to stick together and form larger clumps. Over millions of years, these clumps may grow into asteroids, moons, comets, and planets. NASA observations of protoplanetary disks reveal rings, gaps, spirals, and asymmetrical structures. Some gaps likely form because young planets already orbit within the disk, clearing paths through surrounding material by gravity. Other patterns may result from magnetic effects or uneven gas flow. Scientists continue studying how quickly planets form and how their migration influences the architecture of developing planetary systems. The Orion Nebula remains one of the most closely studied nearby stellar nurseries. Located within the Orion molecular cloud complex, this region contains many young stars embedded within glowing gas and dust. Powerful radiation from newly formed massive stars shapes the surrounding cloud-carving cavities and illuminating layered structures. Observations from multiple telescopes reveal disks around many young stars, some actively forming planetary systems. Young stars often produce strong stellar winds and jets during early development. Magnetic fields channel streams of charged particles outward along the star's rotational axis at high speed. These jets can extend for trillions of kilometers into surrounding space, interacting with nearby gas and producing glowing shock fronts. Such activity helps remove angular momentum from the forming system, allowing material to continue falling inward toward the star. Massive stars influence nearby star formation strongly because their radiation and winds compress surrounding gas, while also dispersing portions of the cloud. Some regions experience triggered star formation, where shock waves from older stars compress nearby material enough to begin new gravitational collapse. Other regions become disrupted before stars can fully develop. Star formation therefore proceeds unevenly across large nebulae. Chemical complexity also develops within molecular clouds. Astronomers detect water, carbon monoxide, ammonia, methanol, and many organic molecules drifting through cold interstellar gas. Some molecules form directly in gas clouds, while others develop on the surfaces of dust grains under low-temperature conditions. These compounds later become incorporated into forming stars, planets, moons, and comets. Not all nebulae form stars actively. Some represent material expelled by aging stars near the end of their lives. Planetary nebulae form when medium-sized stars shed outer layers into surrounding space, creating expanding shells of glowing gas. Supernova remnants arise after massive stars explode, sending shock waves and enriched material outward through the interstellar medium. These processes recycle heavy elements back into future generations of stars and planets. Observations indicate that star formation has occurred repeatedly throughout the history of the Milky Way. The galaxy slowly transforms gas into stars over billions of years, while older stars return processed material to space. Elements such as carbon, oxygen, silicon, and iron originate from stellar processes and later become incorporated into rocky planets and living organisms. Infrared, visible light, radio, and X-ray telescopes each reveal different aspects of nebula structure. Radio observations detect cold molecular gas hidden deep inside clouds. Infrared instruments reveal warm dust and forming stars. Visible light imaging captures glowing ionized gas, while X-rays trace energetic interactions and stellar activity. By combining these observations, scientists construct more complete models of stellar birth environments. Within star-forming regions, time operates across scales difficult for human experience to perceive directly. Individual gas motions may proceed slowly, yet over millions of years, entire clouds collapse, fragment, and transform into clusters of stars surrounded by planetary systems. In 2025, NASA's telescopes continue observing these nebulae, carefully studying how gravity shapes diffuse interstellar material into stars, planets, and the building blocks of future worlds hidden within light, dust, and cold drifting gas. Within the galaxy, some regions contain matter compressed under conditions so extreme that ordinary physical behavior changes dramatically. In 2025, NASA observatories continue studying black holes, neutron stars, and other dense remnants left behind after the deaths of massive stars. These objects cannot usually be observed directly through visible light alone. Instead, scientists examine their effects on nearby matter, radiation, magnetic fields, and surrounding space-time. The observations reveal environments shaped by intense gravity, high-energy particles, and enormous temperatures operating far beyond familiar conditions on Earth. A black hole forms when enough mass becomes concentrated into an extremely small region of space. Gravity near such an object becomes so strong that beyond a boundary called the event horizon, nothing can escape, including light itself. Because black holes emit no direct visible light from within the event horizon, astronomers detect them indirectly through surrounding activity. Many black holes originate from the collapse of massive stars. When nuclear fusion inside a large star can no longer support the star against gravity, the core collapses inward. Depending on the remaining mass, the collapse may produce either a neutron star or a black hole. During some of these events, outer layers of the star explode outward in a supernova, enriching surrounding space with heavy elements. Supermassive black holes occupy the centers of most large galaxies, including the Milky Way. These black holes contain millions or billions of times the mass of the Sun. Sagittarius, A star. The black hole at the center of the Milky Way remains relatively quiet compared with actively feeding black holes in some distant galaxies. Even so, NASA telescopes continue monitoring the region closely because gas clouds and stars orbit nearby under strong gravitational influence. Matter falling toward a black hole often forms an accretion disk, a rotating structure of gas and dust heated by friction and compression. As material spirals inward, temperatures rise enormously and high-energy radiation is emitted. X-ray observatories study these emissions to estimate black hole mass rotation and surrounding conditions. Some actively feeding black holes produce jets extending far into space. Magnetic fields near the accretion disk channel particles outward at velocities approaching the speed of light. These jets interact with surrounding gas and can influence star formation within entire galaxies by heating or dispersing interstellar material. In 2025, NASA continues collaborating with international observatories studying black hole behavior across many wavelengths of light. Radio telescopes, X-ray observatories, infrared instruments, and visible light measurements together provide more complete views of these energetic systems. Observations indicate that black holes play important roles in galaxy evolution, although many details remain uncertain. Neutron stars represent another outcome of stellar collapse. When a massive star explodes but leaves behind insufficient mass to form a black hole, the remaining core may collapse into an object composed primarily of neutrons packed extremely densely together. A neutron star may contain more mass than the Sun compressed into a sphere only about 20 kilometers across. The density inside neutron stars becomes so extreme that ordinary atomic structure can no longer survive. Electrons and protons combine under immense pressure to form neutrons. Scientists continue studying the exact state of matter within neutron star interiors because laboratory experiments on Earth cannot reproduce such conditions fully. Some neutron stars rotate rapidly and emit beams of radiation from their magnetic poles. If these beams sweep across Earth repeatedly, astronomers observe regular pulses of radio waves, X-rays, or gamma rays. These objects are called pulsars. Certain pulsars rotate hundreds of times each second with remarkable precision, making them useful for studying gravity and the behavior of matter under extreme conditions. NASA observatories monitor pulsars carefully because slight variations in their timing may reveal interactions with nearby objects or distortions in space-time itself. Observations of pulsars in binary systems where two stars orbit one another provide important tests of Einstein's theory of general relativity under strong gravitational conditions. When two neutron stars spiral together and collide, they produce powerful events called kilonovae. These collisions generate gravitational waves, ripples in space-time predicted by general relativity, and first detected directly during the early 21st century. NASA space telescopes and ground-based observatories continue studying such events because they create heavy elements, including gold, platinum, and uranium, through rapid nuclear processes. Gravitational waves provide a new way to observe the universe beyond ordinary light. As massive objects accelerate or collide, they disturb space-time itself sending faint waves outward at the speed of light. Specialized detectors on Earth measure tiny distortions caused by passing gravitational waves. Combining gravitational wave detections with telescope observations allows scientists to study cosmic events more completely. Some black holes exist in binary systems with ordinary stars. Gas pulled from the companion star forms hot accretion disks that emit strong X-rays. Variations in these emissions reveal changes in gas flow and magnetic interactions near the black hole. In certain systems, matter occasionally accumulates until sudden bursts of radiation occur. Magnetas form a rare type of neutron star possessing extraordinarily strong magnetic fields. These magnetic fields may become strong enough to distort atomic structure near the surface. Magnetas occasionally release bursts of high-energy radiation associated with magnetic stress and crustal fractures. Observations indicate that such events remain unpredictable and highly energetic. At galactic scale, supermassive black holes may merge when galaxies collide. Simulations and observations suggest these mergers influence galactic structure over long periods. Future gravitational wave observatories planned for space may detect waves from such enormous mergers directly. In 2025, NASA's observations continue revealing a universe where gravity shapes matter into forms far stranger than those experienced within ordinary planetary environments. Black holes consume surrounding gas, neutron stars compress matter beyond familiar physics, and gravitational waves carry information across immense cosmic distances. These extreme regions remain difficult to study directly, yet each measurement gradually improves understanding of how matter, energy, and gravity behave under the most intense conditions known in the universe. Far beyond the nearest stars and nebulae, entire galaxies fill the observable universe in enormous numbers. In 2025, NASA space telescopes continue observing galaxies across vast cosmic distances, capturing light that has traveled for billions of years before reaching Earth. These observations reveal structures ranging from small irregular systems to giant spirals and massive elliptical galaxies containing trillions of stars. Seen together, galaxies form clusters, filaments, and broad patterns extending across the observable universe like a slowly evolving cosmic web. The Milky Way itself is a spiral galaxy containing hundreds of billions of stars along with gas clouds, dust lanes, star clusters, and dark matter. From Earth, much of the galaxy appears as a pale, luminous band stretching across the night sky. Yet beyond the Milky Way lie countless additional galaxies separated by immense distances measured in millions or billions of light years. NASA's James Webb Space Telescope and Hubble Space Telescope continue examining galaxies from different cosmic eras. Because light requires time to travel through space, observing very distant galaxies allows astronomers to study the universe as it existed long ago. A galaxy observed at a distance of billions of light years appears not as it exists today, but as it existed when its light first began its journey toward Earth. Some distant galaxies observed in 2025 formed during the early stages of cosmic history. These young systems often appear smaller, less structured, and more active than many nearby galaxies. Intense star formation occurs within them as gas clouds collapse rapidly into new generations of stars. Observations indicate that galaxy evolution proceeds gradually through mergers, star formation, black hole activity, and interactions with surrounding matter. Spiral galaxies contain rotating disks filled with stars, gas, and dust arranged around central bulges. Spiral arms appear bright because they contain many young stars and active star-forming regions. Density waves moving through the disk help compress gas clouds, encouraging the formation of new stars along the arms. The Milky Way belongs to this broad galactic category. Elliptical galaxies differ greatly in appearance. These galaxies contain older stellar populations and less cold gas for forming new stars. Their shapes range from nearly spherical to elongated structures without distinct spiral arms. Many elliptical galaxies likely form through repeated mergers between smaller galaxies over billions of years. Irregular galaxies lack stable organized structure. Some have been distorted by gravitational interactions or collisions with neighboring galaxies. Others remain relatively small systems shaped by uneven star formation and tidal forces. Observations reveal that galactic interactions remain common across cosmic time. When galaxies pass near one another, gravity reshapes both systems gradually. Tidal forces pull streams of stars and gas outward into space, creating long tails and bridges between galaxies. In some cases, galaxies eventually merge completely, combining stars, gas, dust, and central black holes into a larger structure. Simulations and observations suggest that the Milky Way and the Andromeda Galaxy may merge several billion years in the future. Galactic collisions rarely involve direct collisions between individual stars because stars remain separated by enormous distances. Instead, the interactions primarily affect gas clouds and overall gravitational structure. Gas compression during mergers often triggers bursts of star formation, producing many young hot stars within disturbed regions. At the centers of many galaxies lie supermassive black holes. Some remain relatively quiet, while others actively consume surrounding matter and release enormous energy. Active galactic nuclei emit radiation across many wavelengths, sometimes outshining the rest of the galaxy itself. Jets extending thousands of light years may emerge from regions near the central black hole, influencing surrounding intergalactic gas. Dark matter also plays a major role in galactic structure. Observations indicate that visible stars and gas account for only a fraction of the total gravitational mass within galaxies. The motions of stars and galaxies suggest that much additional unseen matter surrounds them in large halos. Scientists call this invisible component dark matter because it does not emit, absorb, or reflect light directly. The exact nature of dark matter remains uncertain. Researchers infer its presence through gravitational effects rather than direct detection. Measurements of galactic rotation, gravitational lensing, and large-scale cosmic structure all support the conclusion that dark matter exists throughout the universe. Gravitational lensing occurs when massive objects bend light traveling through space-time. Galaxies and galaxy clusters can distort and magnify the light of more distant objects behind them. NASA telescopes use this effect to study extremely distant galaxies, otherwise too faint to observe directly. These natural gravitational lenses help astronomers examine conditions in the early universe with greater detail. Galaxy clusters represent some of the largest gravitationally bound structures in the universe. Hundreds or even thousands of galaxies may orbit within a single cluster surrounded by hot gas and dark matter. X-ray observations reveal extremely hot gas filling the space between galaxies inside clusters. This gas contains large amounts of ordinary matter and preserves information about cluster formation and interaction. Across even larger scales, galaxies form filamentary patterns separated by enormous voids containing relatively little matter. This cosmic web developed gradually from tiny density variations present in the early universe. Gravity slowly amplified these differences over billions of years, drawing matter into clusters and filaments, while emptier regions expanded further. In 2025, NASA observations continue pushing farther into deep space and earlier cosmic history. Telescopes detect faint galaxies whose light began traveling long before Earth formed. Yet many uncertainties remain. Researchers continue refining models of galaxy formation, dark matter distribution, and black hole evolution, as new observations provide increasingly detailed information. Across the observable universe, galaxies drift through expanding space under the influence of gravity and cosmic expansion. Stars form, galaxies merge, black holes grow, and light crosses billions of years before entering telescope mirrors near Earth. NASA's instruments continue gathering this ancient light, carefully revealing the structure of the universe on its largest visible scales. At the deepest observable distances, the universe appears not as isolated stars or galaxies, but as a record of its earliest visible stages. In 2025, NASA observatories continue studying ancient light, early galaxy formation, dark matter, and cosmic expansion in order to understand how the universe evolved from its beginning toward the structures seen today. These investigations reach close to the limits of observation itself, where light becomes faint, stretched, and altered by immense stretches of space and time. The observable universe began approximately 13.8 billion years ago in an extremely hot and dense state, often called the Big Bang. This term describes the rapid early expansion of space itself, rather than an explosion occurring at a single point within empty space. In the earliest moments, temperatures and densities exceeded conditions that can currently be reproduced in laboratories. Much about these earliest fractions of time remains uncertain, because present theories cannot yet fully unify gravity with quantum physics under such extremes. As the universe expanded, temperatures gradually decreased. During the first few minutes, simple atomic nuclei formed primarily hydrogen and helium, along with small amounts of lithium. For hundreds of thousands of years afterward, the universe remained filled with hot ionized gas through which light could not travel freely. Electrons moved independently from atomic nuclei, scattering photons repeatedly. Eventually, the universe cooled enough for electrons and nuclei to combine into neutral atoms. Once this occurred, light could move through space much more freely. The faint remnant of this ancient radiation still fills the universe today as the cosmic microwave background. NASA missions studying this background radiation continue providing important information about the early universe's composition, age, geometry, and evolution. The cosmic microwave background appears remarkably uniform across the sky, yet tiny temperature variations exist within it. These slight differences represent early density fluctuations present shortly after the beginning of cosmic expansion. Over billions of years, gravity amplified these small variations, allowing gas and dark matter to gather into stars, galaxies, and larger structures. Dark matter remains one of the central mysteries of modern cosmology. Observations across many scales indicate that ordinary visible matter represents only a small portion of the universe's total mass-energy content. Dark matter exerts gravitational influence yet does not interact strongly with light. Scientists continue searching for direct evidence regarding its physical nature through laboratory experiments, particle detectors, and astronomical observations. Another major mystery involves dark energy, a term describing the observed accelerated expansion of the universe. During the late 20th century, astronomers discovered that distant galaxies appear to move away from one another increasingly rapidly over time. The cause of this acceleration remains uncertain. Dark energy may represent a property of space itself, or arise from processes not yet fully understood within fundamental physics. NASA space telescopes continue observing extremely distant galaxies, whose light originated during the first few 100 million years after the Big Bang. These galaxies appear surprisingly developed in some observations, leading scientists to refine models of early galaxy growth and star formation. However, interpretation remains complex because distances, masses, and ages involve indirect measurement techniques with important uncertainties. The James Webb Space Telescope contributes significantly to this work by observing infrared light stretched from earlier visible wavelength through cosmic expansion. As space expands, light traveling across the universe becomes stretched toward longer wavelengths, a process called redshift. More distant galaxies generally display greater redshift because their light has traveled longer through expanding space. Some early galaxies contain large populations of young stars forming rapidly from collapsing gas clouds. Others already show signs of structure and chemical enrichment, surprisingly early in cosmic history. Heavy elements such as carbon, oxygen, and iron did not exist immediately after the Big Bang, but formed later inside stars and supernovae. Their presence in distant galaxies helps astronomers estimate how quickly stellar evolution progressed during the universe's first eras. The earlier stars themselves remain difficult to observe directly. These first-generation stars likely formed from nearly pure hydrogen and helium before heavier elements became common. Scientists believe many of these stars were extremely massive and short-lived, rapidly producing heavier elements and influencing surrounding gas through radiation and supernova explosions. Large-scale cosmic structure continues evolving today. Galaxies move within clusters, clusters interact gravitationally, and space itself expands continuously. The observable universe may represent only part of a much larger whole, extending beyond regions visible from Earth. Because light travels at finite speed, there exist limits to how far observation can reach. Cosmologists also study whether inflation occurred during the earliest moments of cosmic history. Inflation describes a proposed period of extremely rapid expansion that may explain the large-scale uniformity of the universe and the origin of the early density fluctuations. Observational evidence supports several aspects of inflationary theory, though the exact mechanism responsible remains uncertain. Black holes, galaxies, dark matter, and cosmic radiation all connect within this broader picture of cosmic evolution. The universe changes over immense spans of time far beyond ordinary human scales. Stars form and die, galaxies merge, and matter slowly reorganizes under gravity, while expansion continues across the observable cosmos. In 2025, NASA's observations reach farther into deep space than ever before, examining light that began its journey near the beginning of cosmic history. Yet even with increasingly advanced telescopes, many fundamental questions remain unresolved. The exact nature of dark matter and dark energy remains unknown. The conditions during the universe's earliest moments remain only partly understood. Observations continue narrowing uncertainties while also revealing unexpected complexity. At the deepest visible distances, the universe appears as ancient light crossing expanding space through billions of years of cosmic history. Faint radiation from the early universe still moves silently through the darkness, carrying information about matter, energy, gravity, and time itself. NASA's instruments continue receiving this distant light, patiently studying the outermost visible layers of cosmic origin at the limits of present human understanding. The universe continues expanding quietly beyond all visible horizons, while Earth turns slowly beneath its thin atmosphere. Across billions of kilometers, spacecraft drift through darkness, carrying instruments, memories, and signals moving steadily between worlds. Around distant stars, planets circle in silence beneath unfamiliar skies. Within nebulae, clouds of gas continue gathering under gravity, preparing future generations of stars that will shine long after present civilizations fade into history. On Mars, dust settles softly across ancient lake beds and volcanic plains. Around Jupiter and Saturn, moons continue orbiting through cold sunlight reflected from ice and cloud. Beyond Neptune, frozen bodies move through darkness along paths established billions of years ago during the solar system's formation. At the edge of the heliosphere, the weakening solar wind meets the sparse material between the stars where Voyager spacecraft continue their slow, outward passage. Farther still, galaxies drift through expanding space while ancient light crosses unimaginable distances toward Earth. Some of this light began traveling before the Sun existed. Some left its source before the Milky Way fully formed. The faint glow of the cosmic microwave background continues surrounding the universe as a remnant from its earliest visible age still detectable after billions of years of expansion. NASA's discoveries in 2025 reveal no final boundary and no complete ending to exploration. Each observation adds detail to a larger picture that remains incomplete. Uncertainty continues alongside knowledge. Measurements grow more precise while deeper questions remain open. The universe appears vast beyond ordinary human scale, yet its patterns emerge gradually through patient observation, careful mathematics, and quiet persistence across generations of scientific work. Above-Earth satellites continue orbiting through the night while telescopes remain pointed toward distant stars and galaxies. Data continues arriving in steady streams from instruments scattered across space. Beneath the motion of planets, clouds, galaxies, and expanding cosmic structure, the universe proceeds without hurry, shaped by gravity, light matter, and time.